Hello and welcome to Petroleum Bites. Today we'll cover one of the most widely applied artificial lift method in the oil industry. It's the gas lift. This technique is especially common in wells with a high gas to oil ratio. We'll start by introducing the concept of gas lift, explaining how it helps unloading wells by injecting gas into the annulus and lifting formation fluid to the surface. After that, explain main component of gas lift system and outline the function of each part. Next, we will walk through the well unloading sequence during gas lift startup, highlighting the changes in unloading valve status, casing and tubing head pressures. From there, we'll move into the gas lift design fundamentals, focusing on how to determine valve depth using pressure gradient of both injected gas and formation fluid. And finally, we will wrap up with the key applications, advantages and limitations of gas lift, offering a complete understanding of its role in oil field operations. So, let's get started. When dealing with a depleted reservoir and the fluid hydrostatic gradient is heavy to allow natural well flow to surface, the well can be reactivated using gas lift as an artificial lift method. This can be achieved by installing side bucket mandrels in the completion string and equipping them with gas lift valves. Gas is then injected into the tubing casing annulus at a design rate and sufficiently high injection pressure. Through the gas lift valve, the injected gas entered the tubing, reducing the liquid column hydrostatic weight. This reduction creates a pressure drawdown, enabling the well to produce additional fluid and deliver them to the surface at the required wellhead pressure. Gas lift completion is made up of three key downhole components. First is a production packer, positioned near the production zone at the end of the tubing string. Its role is to isolate injection gas between the casing and the tubing, while also providing a reliable seal between the casing and the reservoir. Next are the side buckets mandrels, installed at various depths determined by the gas lift design. These mandrels house the gas lift valves without restricting the tubing flow area or intervention access. They also provide communication between the casing and the tubing, allowing injected gas to enter to the tubing. Finally, the gas lift valves regulate gas injection into the tubing. Each valve typically contains a pre-charged bellow that sets valves opening pressures, enabling controlled well unloading. In addition, these valves are equipped with check valves to prevent backflow or produce fluids from the tubing into the casing, ensuring stable and efficient production. Unloading a gas lift well and preparing it for production follows a defined sequence. The process begins with the well in a static condition, filled with the killing fluid in both tubing and casing. All gas lift valves are installed and initially set to the open position. Gas injection starts through the casing, displacing the kill fluid from the casing into the tubing via the open valves. This causes the casing head pressure to significantly rise until the injection gas reaches to the first valve and into the tubing, creating a slight drop in injection pressure. As injection continues, part of the gas moves deeper and breaks through the second valve, leading to another drop in injection pressure. Each valve is preset to close once the injection pressure falls below its design setting, forcing the gas to move more progressively to deeper valves. This step-by-step unloading continues till the gas reaches to the deepest valve, known as the orifice valve. The orifice valve remains open as the final and the deepest gas injection point, reducing the weight of the fluid column and creating sufficient drawdown to allow the reservoir to flow and sustain production. Let's now move to gas lift design. The primary goal of the design process is to determine the number and depth of required valves, along with their operating pressure to achieve the target production rate while working within the limits of available gas injection rate and pressure. Before beginning the design, it is essential to understand the key pressure gradients that govern gas lift design. This include the static pressure gradients determined by reservoir pressure and produced fluid density, flowing pressure gradient, which is affected by tubing length and diameter, in addition to produced fluid property and the amount of injected gas added to produce fluids. Casing pressure gradient, determined by allowable casing pressure and the injected gas pressure gradient. The design process starts by calculating the drawdown needed between the reservoir and the wellbore to deliver the desired production rate. Next, the killing fluid gradient that fills the wellbore is plotted between designed wellhead pressure and casing pressure. Unloading valve depth is identified at the point where the gradient intersects with the casing pressure gradient. The valve opening pressure is adjusted based on the casing pressure at the intersection point. This sequence is repeated and continues until the deepest intersection point is reached, where the final valve is kept open at the operating orifice valve to ensure continuous gas injection during production. With that, the total required number of valves is determined along with their downhole depth and operating pressure to obtain required well production rate. Gas lift offers several advantages and applications that makes it one of the most preferred and reliable artificial lift method for oil companies compared to other alternatives. First, it has a relatively low initial installation cost since it requires inexpensive downhole equipment along with the low operating and maintenance expenses after starting well production. Second, gas lift completion provides full access to wellbore, which simplifies future well intervention and surveillance operations. Third, it demonstrates excellent efficiency in handling solids and gas compared to other artificial lift methods that rely on downhole moving parts such as ESP or sucker rod pumps, which are more prone to issues like pump stuck or gas locking under similar conditions. However, despite these advantages, gas lift also comes with challenges and limitations. Gas lift requires a reliable and continuous supply of gas injection at stable rates and pressure to sustain production. Meeting these requirements often demands significant upfront investment in infrastructure and surface facility to ensure a continuous production cycle. That brings us to the end of today's bite. I hope you found this video informative and valuable. If you have any questions, feedback, or suggestions for future topics, please feel free to share them in the comment section below. You can also reach me directly via email at petroleumbites@gmail.com. I'd love to hear your thoughts and ideas. Thank you for watching and looking forward to seeing you next time.